Good day, ladies and gentlemen, and welcome to our next lecture. Today we're going to be looking at the design of fixed base plates as part of our Structural Design 424 Steel Design course at Stellenbosch University. And so now, today we're going to be having a look at when you've got a column. For instance, we've got our I-beam here that is sitting on a base plate. There's our column. And it is carrying a moment. So there's both a moment and an axial load we're going to design for. So coming down, we have our compressive force, Cu, and then we also have some moment force, M subscript U. So these are ultimate limit state forces applied to our column. And now we need to see how we're actually going to run through the design and get to a stage where we can safely give a base plate thickness, because the most important thing as a designer, you would have calculated your moment and your compressive force from your structural analysis, and now you get to the place you have to answer the question now, how big is my base plate and how thick, what size bolts do I need? What size holding down bolts do I need? So we're going to start working on this. And to simplify the main behavior, the design calculations basically work out as follows. As the load is applied, the section rotates and you create a compression block on the one side. So the section I'm hatching now in green is there would be a solid continuous compression and basically nothing outside of that. But then on the other side, you would have tension at the bolts. So to simplify this, well, to look at the cross-section, here once again, there's our cross-section. So we've got a force, we've got a moment. And underneath this base plate, we are now going to have some compressive force on the one side. And on the other side, we are going to have a tension force reaction. And this is carried by the base plates. By the HD bolts, the holding down bolts on the one side. And so we're going to call that TB, capital T. So that's the tensile force in our holding down bolts. On the other side, simply to make our subscripts and our calculations easier, I'm going to simplify this equation, this compression block, to call it C subscript C. So that is the compressive force due to the entire compression block, and that will act at the centroid of the rectangular stress block. I'm going to start labeling this diagram now with all the important parameters that we will need when working this out, because as I said, the important thing we need is our dimensions of our base plate, so a breadth there, and then a depth of the entire section that we will need. We're going to call this D. Actually, let me just illustrate. The main thing we're actually interested in is the depth to the where the HD bolts are acting, and I'm going to call that D1, and that's quite an important value we're going to use soon, and also D2, and these you'll normally need to calculate. If you don't have a base plate size, you'll have to assume a size and then calculate D1, D2, and then gradually get to a stage where you can calculate them. This depth of the compression block we're going to call X, and now that we have our main parameters, the main things we need to solve for are X, and we also need to solve for TB. So those are what we need ultimately. Those are the important values that we would like to calculate from our overall workings now. So I'm going to start carrying out the equations on the side, and the first important thing is just to list what are our assumptions. So here are assumptions, because everything we do will be based upon these. I'm just going to now write them all out. Okay, so these are our assumptions. Firstly, that we assume that the bolts only carry tension. So if there is compression on them, we just ignore them. So having a look at the side, you'll see is on the right-hand side, I've totally ignored the bolts. It doesn't matter whether they're there or not. And on the left-hand side, they are only carrying a tension. They are carrying that force TB down. The next thing is there's a uniform compression of 0.6 FCU, so 60% of the concrete cube strength under the base plate. So that is this hatched green value. So this value here is 0.6 Cu, so that's 60% of our concrete strength. Then thirdly, we're going to use a rectangular stress block. However, this is not compulsory. This is adjusted if TB is known or to suit what we will call C values, which we covered in the pinned base plate section previously. And basically what it is that we normally, as I said, have a rectangular stress block here, that all the way around. However, if we knew the thickness of the base plate, we could, for instance, I'm going to draw and then delete something, work out how far the load could actually spread. So for instance, if we had a 10 mil base plate, it might not be able to spread to the end of the base plate, and we'd have to have a revised shape, as I've shown within that blue line, but it would depend if we knew what the thickness was or not. Normally you don't. Normally you calculate the thickness and you make your design suit your assumptions. Well, you assume a rectangular block and then make your base plate thickness sufficient for that. Now that we have our assumptions, what we're going to do is start calculating those unknown values I was referring to. So we're going to take equilibrium at the base of the column about the bolts, because we've got two unknowns, so we want to get rid of them. So if we take the sum of moments about our bolts, the bolt's force disappears from the equation. So there's plus. So coming back, I'm going to take sum of moments about that point I've just illustrated. So you will see that we're going to have terms with mu, cu, and then this resultant force cc appearing in it. So as I said, so positive is that direction, clockwise, so mu plus cu times d2. And depending on how things are applied, M and C and such may go positive, negative, etc. Well, if there's a tension force, then obviously it'll be acting in the opposite way. Then minus cc, and then the centroid of that force is d1 minus x over 2 from the side, and this equals 0. And so to simplify this, our mu plus, I'm just going to substitute the values into this equation for the cc. So this is just the area times by our stress. And that gives us our full equation we can work with. And so, as I said, and so the BP, the breadth of the base plate is there. So I'm just to be consistent, this should be the breadth of our base plate. And so there is our equation that governs the design. At this point in time, we do have two terms. X does appear in this equation twice. So we end up with a polynomial. And so we would have to solve for x. Solve for x, and solving our polynomial. So we did have a look in the previous video for the pinned base plates how to do that. And but once you have x, you now know what the compressive force is. Now determine TB, determine the force in the bolts. And we're going to do this, we're going to take sum of forces vertically equal to 0, being positive, and from that we would ultimately end up with so we end up being able to calculate the force in our base plate as the compression block minus our applied force. And once again, if there was a tension, we would just swap it around. So that would give us our value underneath. So if a realistic value not found, then resize the plate. Resize the base plate, because it is possible that you would have no solution if the base plate is too small for equilibrium, then you may need to redesign it. So I'm just going to come back and look at now how the structural mechanics actually works. So there's our base plate. Once again, we had a moment and a compressive force. But if we have sort of a look at the stresses and strains under the base, what you will find that occurs here is that on the one side you have tension occurring, and on the other side you have compression occurring. And if I just sort of draw a straight line between the two, you have that. And so here you will have the strain in the compressive block, strain in the tension HD bolt, and on the other side you've got your strains in the area experiencing compression. So that gives you a positive compression reaction. On the other side you've got your negative, so your tension force in the bolts. Now, when you work with that, you end up, as I said, with the stress below the stress below the base plate, but we simplify it into a rectangular block. You'll see that even though there's a wider area experiencing compression, we only use a certain area. And you can think of this as just sort of simplifying a nonlinear stress-strain graph, because a concrete material taken all the way to failure, it would look something like that. But this is, as I said, this is a stress-strain graph of concrete accurately, but what we are doing is we are just simplifying that into a uniform block. And that gives us then the behavior. That's why we assume we have a uniform stress, and with including partial factors and all the rest, we have the 60% of the yield stress. So that is our assumed distribution, where on the other hand, the blue is a more accurate distribution. But that gives us our nice, easy to use rectangular stress distribution, which we can design from. But now we need to start determining the thickness of our base plate, because we've got this base plate here. I just want to add a label to it. We have an unknown thickness here, which is the thickness of the base plate, and that's what we're trying to determine. But if we have a look at this plate, one thing you can imagine is that as this force TB pulls on it, this is going to try bend down, whereas on the other side, it's going to try push up. So we've got two failure mechanisms that we need to predict, one on the one side where there's tension and the other side where there is compression. And we need to now describe that condition by finding what is the moment at the face, and then from there we can calculate what thickness of base plate we need. So I'm going to start doing that, start determining TB. That is the thickness of the base plate. Determine thickness of base plate. And the diagram we would end up using looks something like this. We've got our flange of our column, we've got our base plate, and then we've got our other flange of the column coming down, and there's a section through. And as I said, we've got our one force on the other side, on the one side TB, and on the other side we have a compressive force pushing up. Now, this stress may or may not occupy this entire distance to the end of the base plate. It is possible that you may only have a short section like that at the end. You may not have stress under the whole, or going past the flange of the column. So it really depends. But if we now have a look at that diagram, and I plot what the bending moment diagram through the section looks like, we'll end up with something like this. So there's the bending moment on my tension side, and there now I'm going to draw the bending moment diagram on the other side, but I'm going to plot down. It will go right to the face, because it won't fail beyond the face, because it provides an infinite stiffness, the column coming down. But that gives us our resistance, because effectively what we can do is model this as a cantilever sticking out with a uniform load sitting on it. And on the tension side, it's quite straightforward. This value here is simply that times some distance m, where m is the distance outside of the flange coming down there. So that will give us then the force at the column, where on the other side it depends. So I'm going to have two equations now that I'm going to use for the compression side. So on compression side, as I said, there are going to be two different setups. If x is less than c end, and what we're going to call this is the end distance. So if the x is less than c end, what you have there is you've got a cantilever, but with a non-continuous distribution of stress below, like that, meaning that your resultant is there, but then you have an area of zero stress outside of it. And so here, what we need is our x, and our x plays prominently. Once again, there is our C end. And so our equation to deal with that, the moment at the face, so the moment there, is a function of the stress times by the width times by x. That now gives us the force, this red line, times by the distance, C end minus x over 2. However, if x is greater than C end, then we have a different scenario. Once again, we model it as a cantilever, but the load goes past it, meaning that there's simply a continuous 60% of concrete strength, concrete stress on it, and our x goes well beyond. We only use now what is outside of this zone, meaning that our moment is 60% times by our breadth times by now C end times by the lever arm, which is C end over 2. So that ends up with a C end squared. So this ends up with 0.6 over 2 times our concrete strength times by the width of our base plate. So that gives us for this. Now, that gives us a moment at the base plate, at the edge of it, at the column interface. So now we need to solve for TB with our moment of resistance must be greater than our ultimate moment, and our moment of resistance is phi ZPL Fy. And once again, this I discussed in the previous video looking at pinned columns, but it is the breadth times the thickness squared times yield strength, and this is our ZPL value over 4, and we will use that to calculate our moment of resistance. However, now this covers only the compression side. We now need to go onto our tension side. So once again, on tension side, this side is a little bit easier. What we do, just to illustrate what's happening here, I'm going to go back to our diagram. We've got our force pulling down. We are going to work with a width all the way along there, and just assume that that is resisting the load. It's the same thing as previously with the compression side. We were using that width there and checking the capacity of that plate along those dotted blue lines and making sure that that capacity is sufficient to resist the bending moment we've got. So now I'm going to go back to our diagram. back to our calculation. So on tension side, our moment, as I said, was much easier to calculate now. So it's just the force times the distance. And at failure, we need to make sure that the moment is less than or equal to our resistance, which we've calculated above. This is a laterally restrained, well, it's a section that does not experience buckling because this is a section bending about its weak axis. So that means our thickness of base plate will be greater than twice, and then this term times phi. And this is according to SANS 10162 and the South African Green Book from the Steel Institute. So that gives you the equations to take through to calculate the thickness and properties of a base plate. So just in summary, I'm going to go back to the diagram. We took our base plate, we assumed a rectangular stress distribution, the green area, but it doesn't have to be rectangular, it could be just about anything depending on the column. And then what we did is we solved for x and we solved for TB. So those, yes, we have solved for them now. We know what they are. Once we have got those, then we worked out what is the moment at the face of the column. So the moment where it will fail and the moment where it will fail. And then from that, we could then get to our thickness. And then finally, we could calculate what our thickness of the base plate is. So thank you. That takes us through the design of a fixed base plate, a base plate that has to carry a moment as well.